Friends, right now we will be going into the modern form of the periodic table, which is called as the modern periodic table, which is also called as the modified form of the periodic table, because here in this specific case we will be having a situation wherein the earlier periodic table, which was given by Mendeleev, which is a short form of the periodic table, was modified, and hence it is also called as modified form of the periodic table. It is also called as Moseley's periodic table. So the same thing is known by three different ways. So you shouldn't be getting confused with the name of this type of periodic table. So in the modern periodic table, the basic difference will be in terms of the periodic law. In the case of Mendeleev, we had seen how Mendeleev had arranged all the elements in terms of the increasing atomic weights, and his conclusion, which was his periodic law, was that the physical and chemical properties of elements are a function of their atomic weights, and that is how we have a difference between the Mendeleev's periodic table, short form of the periodic table, Mendeleev's periodic law, and the modern periodic law. As you guys already know, in the case of modern periodic table, which we are going to study here, as you can see in front of you, in this modern periodic table, we will be arranging elements not in terms of their increasing atomic weights, but in terms of increasing atomic numbers. And hence here, because the elements, as you can see, are arranged in terms of their increasing atomic numbers, as we move from left to right, once a particular period is finished, then we start with the second period. The second period is finished, then we start with the third period, that way. So once we realize that here in the case of the modern periodic table, elements are arranged in terms of their increasing atomic numbers, hence we can give the modern periodic law, which is derived from Mendeleev's periodic law. That is, when elements are arranged in the increasing order of atomic numbers, we can say that the physical and chemical properties of elements are periodic functions of their atomic numbers. In the case of Mendeleev's periodic table, it was a periodic function of their atomic weights. So I hope so, my dear friends, you understand the basic difference between the short form and the long form of the periodic table, which is, instead of atomic weights, we simply write down atomic numbers, then we get long form of the periodic table. That is the first thing. The second thing, let us start with the genesis, how the long form of the periodic table was put forward. What was the origin of that? The origin of that, my dear friends, was very fundamental. By the time the long form of the periodic table was given, by around the year 1916, by Moseley, who was a scientist and on whose name the modern periodic table is given. However, there was a lot of basic fundamental work by other scientists, because of which Moseley could give his modern periodic law. So the work done by other scientists was in terms of discovering a lot of elements which were earlier not known during Mendeleev's time, in the earlier part of the 20th century. So here we had, in the long form of the periodic table, when it was given, we had total of 94 elements which were naturally occurring elements, which were represented in the periodic table as well. So we also had some other elements, like after uranium, which is called as transuranic elements. Those elements were artificially or synthetically prepared. So in the case of Moseley, how he discovered the periodic table, let us first look at that. What Moseley had done is that he had, because of the availability of large number of elements, he was helped in understanding better the correlation between the classification of elements and their periodic physical and chemical properties. So what Moseley had specifically done was that he was the first scientist to plot a graph between the frequency of the emission, which was given by in the form of X-rays, when different elements were bombarded by the cathode rays. We all know how X-rays are formed, right? So when X-rays are formed, the cathode rays, which are incident on the when the X-rays are to be formed, we also have an emission which is given out, and there will be some amount of frequency which will be associated with each type of emission which is given out when each type of different element, each different element is bombarded by cathode rays to form X-rays. So the X-rays which were formed when different elements were bombarded with cathode rays were having a different frequencies, and those frequencies, Moseley had plotted those frequencies of the rays of the emissions which were given out during X-rays emission. He plotted the graph of those emissions, plotted the graph of the frequencies of those emissions along with the atomic weights, but he couldn't find out much of a correlation or much of a repetition of properties. So what he had done is, just for experimental purposes, he plotted the graphs of the frequencies of the emitted X-ray radiation against not of atomic weights but on atomic numbers in his second instance, because first when he tried with atomic weight he couldn't get much of a result. Hence he plotted a graph with atomic numbers, and he achieved the result of his life, wherein there was a clear-cut straight line graph between the atomic number and the frequency of the radiation which was emitted by the X-rays. So as you can see here, it was a huge hit, it was a huge success, his experimentations, and due to which Moseley now concluded that the atomic number and not the atomic weight was one of the fundamental properties of the atom. Now also, as I have already told you, by the earlier part of the 20th century, by the time Moseley had given his theory, the atom was discovered to, was researched to a much larger extent. Quantum physics had taken birth. So we knew at that time what was the exact structure of atoms like, where were the electrons, what were the neutrons, what were the electrons, and what were its area wherein they would be located, and what were their masses, etc., etc., which helped Moseley a lot in understanding the interrelationship between the atomic mass and the periodic properties in terms of physical and chemical properties of different elements. So here, when we have now understood that atomic number is a much more fundamental property than atomic weight in understanding the classification of elements as well as understanding the periodicity of different elements. Now here we have the modern periodic table right now in front of us. Now here we need to understand that in the case of Mendeleev's periodic table, the horizontal rows were called as series, but as you can see here, the 7 horizontal rows which are present in front of you, they are instead of being called as series, they are called here as those are called as periods. So these are like 7 periods which are present in front of you, and we have vertical columns here, that is 18 in number, and these vertical columns, they are called as groups now as well as by Mendeleev. So there was not much of a difference. The difference between the two periodic tables are in terms of the naming of the groups. In the case of Mendeleev's periodic table, as we have already seen, the naming was done in terms of Roman numericals, wherein we started with 0 and then in Roman numbers 1, 2, 3, 4, 5, 6, 7 were written down. However, in this long form of the periodic table, earlier the periodic table was also written in terms of Roman numbers, wherein we had 0 group elements, then we had 1A, 2A, 3A, then we also had till 7A, then we also had then B group elements, wherein we have 1B, 2B, 3B till 8B. So the point, my dear friends, is that IUPAC had changed the naming, the nomenclature of the vertical columns which are present, which are called as groups of the periodic table. So therefore, in the case of modern periodic table, instead of using Roman numericals, the IUPAC had changed the method to 1, wherein simple numbers were used. That is, simple numbers like 1 to 18 were used because there are 18 groups in the modern periodic table, right? So we simply write it down in terms of numbers as it is shown in this periodic table. Simply like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So therefore, there are total in terms of 18 groups as you can see, and there are in terms of periods, there are 7 periods in this periodic table. In this periodic table, in this modern form of the periodic table, earlier there were, when the modern form of the periodic table was formed, there were like very less number of elements, like around 105. Right now we have more than 118 elements which have been discovered, and in this periodic table, as you can see, when it is in its saturated form, it can contain a total of 118 elements. As you can see, in the first period, we have 2 elements, which is starting from hydrogen and finishing with helium. In the second period, we have we have a total of 8 elements, as you can see, and we have the elements starting from lithium, and we are finishing with neon, which is a noble gas. As you can see, each period will be starting with an alkali metal, and it will be finishing with a noble gas, which is present on the extreme right hand side of the periodic table. As you can see on the penultimate group of the periodic table, we have the halogens which are present in terms, as you can see, from like fluorine, then we have chlorine, then bromine, then iodine, then acetine. So these are all the halogens which are present in group 17, which is exactly close to group 18, which, as I've already told you, in which all noble gases are present. In the third group, in the third period of the periodic table, as you can see here, it will basically contain also 8 elements. In the again starting with alkali metal, like we have sodium, and finishing with the noble gas argon. In a similar way, we have on the fourth period of the periodic table, we have total 18 elements, because we have the starting of D group elements also, because in total we will be having 2 elements in this period. In the fourth period, we will be having 2 elements from the S block. There will be 10 elements from the D block. There will be again 6 elements from the P block, giving you a total of 18 elements in this one period of the periodic table. So therefore, here we have a building type of structure, as you can see here, wherein we have different blocks. It is very similar to a situation wherein you have a society which has multiple buildings here. So as you can see, the first building which is shown here is like is that of S block elements. The next building, which is which starts in the lower part, is called as the D block elements, which is much more larger, is much more flatter. It is called as D block elements. Next, we have P block elements here, which is another long building here, which contains 7, which is total of 7 floors which are there, including the ground floor. Now we also have, as you can see in the lower part of the periodic table, a basement, where this periodic table finishes, below which you guys know basement, right? So in that basement also we have 2 floors. One is the ground floor and one is the first floor. So these elements are called as lanthanides, and these elements, they are called as actinides because of the name of the element with which they start. So here, as you can see, this is the basic structure of the periodic table. Again repeating, this is the S block, then D block, then P block element, F block element. So the total there are total 4 blocks of the periodic table. The periodic table is basically arranged, as you would surely come to know when we do the chapter of atomic structure. You will understand that this periodic table is arranged on the basis of the electronic configuration of elements. That will be much more clear to you as we move ahead, because the periodic table can be perfectly be written down if in case you know the electronic configuration of any element. For example, if in case you ask me with to point out at the particular location of the periodic table where an element with atomic number with a known atomic number will be present, I can exactly pinpoint the location for you. On the other way around, if in case you show me any spot on an empty periodic table, and if in case you ask me what will be the atomic number of that element in that specific spot, I will be able to tell you very simply by simply adding the number of elements which are present in the different in the different parts of the periodic table, or in the different blocks of the periodic table. Again, if in case we quickly finish off this periodic table, we in group 5, in the fifth period of the periodic table, we again have a total of 18 elements. So the first period of the periodic table had 2 elements, next had 8 elements, then third had 8 elements, fourth had 18 elements, fifth also has 18 elements, sixth and seventh are incomplete periods, wherein they will in total they will be having 32 elements in the 6th and 7th period. Now, how would those 32 elements come? We are already familiar with the 18 elements, right? 2 elements of S block, 10 elements of D block, and 6 elements of P block. In addition to that, we will be having a lanthanide series, which will be also be accommodated in the sixth period of the periodic table, and hence the 14 elements of the F block of the first series of the F block, as you can see here, will also be accommodated here, and hence we have a total of 18 plus 14, which is equal to 32 elements, which will be placed in the 6th period as well as in the 7th period. In the 7th period, instead of lanthanides, those 14 elements in the F block, they will be called as actinides, and those 14 elements in addition to these 18 elements which are already present will give us a total of 32 elements. So therefore, we have 32 elements in period 6 and period 7 of the periodic table. Now, in the first period of the periodic table, we had only the S block elements. In the second and third periods, as you can see, we have S and P block elements both. In the fourth and fifth period of the periodic table, as you can see, we have S block, we have P block, and also we have in between the D block elements. Finally, in the case of 6th and 7th period, we have the S block, D block, P block, and in addition to that, we have F block also. Now, we will be understanding, what is the basis of the different blocks of the periodic table. It is very simple. In case of S block elements will be those elements in which the last electron to enter will be entering inside the S subshell. In the case of, say for example, P block elements, all the different blocks will be defined in a very similar way. P block elements are those elements in which the last electron enters the P subshell. D block elements will be again those elements in which the last electron enters the D subshell. F block elements similarly will be those elements in which the last electron enters the F subshell. Now, what is the basic meaning of orbitals, subshell? All those things I'll be explaining to you in another chapter, which is called as atomic structure. But as of now, let us complete this Moseley's long form of the periodic table, also called as a modified or simply the long form of the periodic table. So here, as I've already told you, we have a total of all the groups are mentioned in terms of numbers and not in terms of Roman numericals. So the drawback of the modern form of the periodic table is very obvious, as you can see. The obvious drawback here is that here, if in case we have 6th and 7th period, we don't have all the 32 elements which are present in the 6th and 7th period, which are placed together. We have this in the case of the 6th period. As you can see, we have a situation wherein 18 elements are present in the 6th period, and then it is incomplete here because we have a total of 14 elements which are present in the lower part of the periodic table, which has to be added along with these 18 elements. So basically all the elements should be in a particular period, should be placed together, right? It looks better. However, In the case of the modern periodic table, we have A block elements which are a part, the first series of the A block elements, which is a part of the sixth period of the periodic table. They are kept separate, and that will obviously be a disadvantage of the modern form of the periodic table. Unfortunately, up till now, there has been no solution to this problem which is encountered. And see, basically, a lot of people have, or a lot of scientists have given a lot of modifications in the long form of the periodic table. So long form of periodic table is now taken as the basic standard, and in which small modifications wherever required has been done, and also will also be done. Like, because of total 118 elements in the periodic table with which the periodic table is saturated, now there are 109 atomic number with 119, and so on. They are being discovered as of now. 119 atomic number has already been discovered. So again, there will be a problem about where to put those elements which are now newly discovered in the periodic table, because by 118 the periodic table is saturated now, right? So where to put element number 119? That will also be another challenge which has to be faced by the periodic table, and due to which the modern form of the periodic table has to be modified accordingly. So there are again different periodic tables which are used in different countries, but International Union for Pure and Applied Chemistry, which is also called as IUPAC, it has given a basic and the most reasonable type of periodic table, which is the most easiest to understand and which makes much more sense and logic. So this is the modern form of the periodic table, which will be, this is an international standard in whichever countries you go. However, you might find in some countries wherein the periodic table has been arranged in slightly different way because of their opinion that that is their way is a better way of understanding the classification of elements.